All right. Hello, everybody. Welcome you to our last technical session of this summit. We will now hear two talks about security. I'm very happy that we have Éric Saliba here for our first talk. He's the head of the scientific and technical division of the French National Agency for Information System Security. We're very much looking forward to your talk, Éric. Please.
Thanks a lot for your invitation. So in my speech, I'm going to give you a very short overview of hardware security and how we see RISC-V as a pretty good enabler for research and development activities. And I will do it based on some ANSSI's projects. First, I wanted to give you a sum up of the technical challenges. The first one is pretty obvious and concerns the implementation of hardware-based security functions. The main purpose of this technical challenge is to develop a secure hardware foundation for the system and the products. Usually it concerns some specific functions like early stages or protection of the cores, but also the problem of the management of the balancing between performances and security. The next one concerns secure by design. It's pretty well known today, and the goal is to improve the assurance level. So mainly using tools for verification, but also to try to have a better control on the design, and also better control concerning the configuration of the security functions. And the last one concerns the coupling between hardware and software security. That means the needs of some mechanisms, hardware mechanisms, to support the software and to improve the security of the software. Next, concerning the security features, we can, I would say, divide them in two blocks. The first one is somewhere design specific and address, I would say, something pretty usual, the core, the interconnection, and the peripheral. And the second block is more specific and concerns some security functions that are really related to the physics and the technology we use in the development. It's, for instance, the case for the true random generator, and also all the topics around the physical attacks, the hardware attacks. In regard of these features, we have the two usual suspects that we see in the security evaluation and security products. I mean the secure elements and the system on chip that are used in different products like smart cards and smartphones, and are used in secure communication, secure computing, and more in more commercial services like wallets. So we have to design the security to choose the technology, but also we have to consider the production, the industrialization, and all the supply chain around this matter. And the last point is, of course, that when we implement the hardware security, we have to consider hardware attacks. That means side channel attacks and fault injections. But more and more, some more cross software and hardware attacks that we consider in microarchitectural attacks. What we do when we consider our activities inside the agency. So we are working on two different kind of projects, collaborations. So I will present two projects in that category, and also contributions to funded projects. And so I will present two projects in which we are partners. And our interest concerning what we see, what we are, I would say, studying, and the survey we are doing today in this matter concerns the security of the core of the processors, and we are making some survey around some projects, and also secure circuit design. It's pretty important for us, and specifically for the mobile applications. And also all the tools that can be used to improve the assessment of the security, the verification, the proof of the security. Concerning so the first project in which we are involved, this project was at the beginning an internal project, so its name is IPECC, ECC for elliptic curve cryptography. So it's a hardware accelerator. So it was designed to implement ECC acceleration, but also countermeasures against some specific attacks, hardware attacks, like side channel analysis, and with the capability to activate and deactivate those countermeasures. And the purpose of this project was to propose a platform on which some users, like academics, for instance, can develop projects and studies to increase their knowledge concerning hardware security and attacks. This design is not techno-agnostic. I mean, it was designed and implemented to be integrated on FPGA or ASIC. Of course, when we consider some specific services like TRNG or physical attack, it's of course techno-specific, and but if we consider only the design, it's fully usable on FPGA and ASIC. So it's what we've done. So we already did two implementation. The first one was on a SOC FPGA with an ARM processor, and the second one was a full FPGA with a RISC-V CVA6. What is also interesting, IPECC can be used with another project of the agency. So its name is libECC. It's a library, so you can plug the library with IPECC. And today we are working with CEA on another implementation, in a full ASIC implementation of the project based on the RISC-V and using, of course, the IPECC. The second project, the second collaboration with INRIA and CEA concerns crypto agility. That is pretty important today, considering the post-quantum cryptographic transition. So the goal is to be able to switch crypto system without changing the hardware. And so at the beginning of the project, the partner decided to select two crypto systems, so MLKM and HQC, and to define a design that can be used by both the two crypto systems. So today the design is done. Its name is Phoenix, and currently the partners are working on the way to integrate this design in a processor. So basically, following two possible strategies, not exclusive. The first one is to integrate it inside the core, and the second one is to do it externally to the core. And we are, for the moment, working on the second option. That could be also quite interesting to do it with an ARM processor. We are also working on on funded project as a part of the consortium. So the first project is the Arsene project. So this project is funded by the France 2030 package, and is part of the priority research programs and equipment. It's a pretty huge consortium with a lot of academics. It's overseen by CEA, CNRS, and INRIA. The main focus is the security of the core of the processor, so 32 bits and 64 bits, sorry. And also to secure the integration of the processor in the system and chip design. There is also a study concerning tools for the secure codes and secure kernel, and also the development of FPGA and ASIC test chip to perform some demonstration and validation. What is the contribution of the agency in this project? So we plan to work on the, I would say, attack on the 32-bit implementation, so physical attacks, I mean. We also contribute to the securization of the 64-bit application processor. We are really interested by all the implementation that can be used in smartphones, to be simple. And we are also concerned and working on the integration of cryptographic algorithm through the ISA to improve performance and security balancing. Our interest in this project, of course, is the availability of open hardware and secure elements that could be protected against high-level attackers, that a range of attackers that we consider. And also, as I said, very interested by all the processors that can be used in mobile application, I would say mobility in general. And also very interested by contribution to the test chip that will be produced during the project and to have some technical analysis, practical analysis on it. Another project, forward project, that is quite new. It was launched this year at the beginning of 2025 or at the end of 2024. So this project is also funded by France 2030 package. It's part of another program, so the Cyber Campus Transfer Program. The consortium is smaller, but we have industrial partners with Safran and Thales. The main challenge is the formal verification of the countermeasures. So it's quite interesting. What is also relevant is the characterization of the robustness of the countermeasures, and also the quantification of the gap between what we see when we are in experimentation with a real product and a formal verification. And so to see what is the gap between the two analyzed. Our interests, so no contribution because the project is quite new, but we are really interested by this project. So of course the application of the use of formal verification methods to the hardware domain, we are pretty well. We know the use of that kind of methods for software analysis, but we really think that it's also very interesting for hardware development. Also to develop a methodology to validate the security and the benefits of the countermeasures, and also to, as I said, to define the gap between the experimental analysis and what the formal methods and the formal verification can really give before any development and test chip production. I think that's all. That's my. I give you the reference of all the projects I named during my speech. And it's time for me to ask you if you have any questions and to thank you for your attention.
Thanks a lot, Eric. Do I have time for one or two questions? Are there any questions from the audience? There we go.
Yeah, good Hello. Good to see, you guys working on the enclave stuff, very similar to the Open Titan project run by the Google side. So my question is that you got all the hardware. What about the software platform? So what about the compliance with the global platform? All the used to be Java car system related. How's the software platform on all your test tube?
You mean what are the work concerning the software part of the...
Yeah, exactly.
Yeah.
The software platform, the global platform compliance, API, all this, right? And assuming, as you say, you support wallet, they support and a secure boot and blah, blah, blah. It's very similar to the ARM security enclave IP. But they always come with the Oracle Java car platform. So.
Maybe the picture is a good answer to your question. So software is, of course, a very important aspect of the security. So there are also a lot of projects on this aspect. But hardware is really a key point on which you have the foundation for the rest. And maybe I'm not sure to really answer to your question, but of course, software aspect is also very important, and we have some project on it. We don't depict the project today, but there is project on it. But what is really important is also to have hardware based on it. We can really build a secure foundation for the software and for the systems.
Yeah, and also another point is that security is about the integration of the whole manufacturing process. Because I used to run the Huawei mobile phone, the whole security compliance, and to meet the because it involves key management and then TSMC and then your laboratory, all this certification stuff. Will you guys consider provide that kind of solutions,
Yeah, what is interesting for end users is to be able to control the configuration of the security. In the first step, some end user want to understand what is in the design, in the hardware and in the design, but also to be able to configure the security of the design from the very, very early stages of the implementation.
I don't think probably you haven't answered my question. Is because I make laptops and I want to use your chips or I want to contribute chip your SoC and I need to sort it out the whole TSMC the fab process.
Okay, so to be clear, what do you want me to explain?
I mean, will you? Is it just a research project and we will never?
Yes, it's fully a research project.
So we will not be going down to the
funded by France, and so we are in a consortium. Okay. And for the collaboration, I explained, we are working with entities and partners. And if some other partners want to work with us, we can study some proposal, but we choose.
Okay, great.
Thank you.
I think you also, Eric is still there afterwards, right?
Yes, we can discuss also,
right? Thanks again, Eric, for the very nice talk. Thanks again for being here.
Yeah, thanks.
Okay, thanks a lot. Okay.